Hi everyone, I'm Viral Shah. I'm one of the creators of the Julia programming language, and I'm not sure, if I've spoken to an audience that's typically not a data science audience, but this is I'm in a DevOps track, so I'm going to try hard to see how I can tailor a talk, for you guys. But maybe just a quick raise of hands of, has anyone heard of Julia before you saw the talk? Okay. How many of you have done 1 plus 1 in Julia? Okay. All right. I'm assuming everyone's kind of used a little bit of Python, some shell scripting, stuff like that. Is that a fair statement? Yeah. Any users of things like R or NumPy? Yeah? Okay. A few users. Okay. So what I'm going to do is I'm going to do a talk that's like more of an introductory talk for Julia, and typically I jump into the presentation, into a demo right away. But I might just use a little bit of a presentation to motivate why Julia, and you guys can just tell me if you need me to go fast or if you need me to go slower. All right. So here goes. This should go full screen or no? Alright, this is kind of like the boring part of the talk, like it's a presentation, so I'm just going to go through it really fast. It's mainly sort of to have some of you folks who may have not heard of Julia before, or maybe have heard about it, read it. How many of you saw it on Hacker News? Like, nobody here watches Hacker News? Okay, a couple of people. Yeah, I thought like you just can't miss that stuff. All right. So Julia is actually a language for technical computing, which means if you are working with a lot of data, or if you're working with scientific computing, if you're working with a lot of real-time data from sensors, big data, whatever you have, if you're working on scientific computing applications or numerical applications, Julia is the latest programming language in that space. This is actually the last 25 years of technical computing, and you might have heard of some of the large fonted languages here, but there's actually about 40 of them out there over the last 25 years. And there is no mention of C or Fortran on these slides, which are the most dominant languages in this field, and that's because this is a list of dynamic languages for technical computing. So people who do technical computing love dynamic languages, just like everyone loves to use Python or Perl or a scripting language, right? You don't want to be necessarily always in a strongly typed language for when you want to write productive code. But essentially the reason why we started Julia we started working on Julia in 2009, and it's been about 6 years now. It was 4 of us originally, Professor Alan Edelman at the MIT department, at the MIT Mathematics department, Jeff Bezanson, Stefan Karpinski, and myself. And the 4 of us started this mainly because we were using various versions of many of these things before, and back then it was believed that you could either have a programming language that was easy to use and productive, or it was fast. So you could use Python and do your numerical computing, and it was okay, or it was but if you had to write for loops, if you had to worry about memory utilization, if you wanted to put it into production, if you wanted to scale it up, then you rewrite your Python programs in Fortran or C. Similarly in businesses, you will often see that people write codes in. So you'd often see people write exploratory code in languages like R and then translate it to Java for production in many deployment scenarios. And so you were always told, it was almost believed to be like a law of like a law of nature, like that you could not have something that is at the same time fast as well as highly productive. And that's kind of where we started Julia from. And so now why is Julia at the same time easy to use? Why is it a dynamic language that's easy to use? At the same time, why is it also high performance and achieves has sort of achieved this larger community over this short time frame? So Julia is The community, the Julia community, is estimated at around 150,000 users right now, and if you go to our GitHub page, you'll see. All right, let's just give up on this thing here. So if you go to GitHub and Julia, you will see it's a pretty large project. So about it's closing in on 500 contributors now, and while there's a long tail of people who've made a single commit, there are about 30 or 40 contributors who have really contributed to Julia in a big way. You also have it's just been going on 30,000 commits, lots of stars. So it's kind of becoming increasingly popular. It's taught by it started about dozens of universities today, where largely taught in engineering classes or in the sciences, and not so much in the computer science parts of the university. So you're beginning to see lots of people graduating with Julia skills, and it was essentially because people thought that there was this law of nature that you can't be fast as well as productive at the same time. When in 2012 we published our Why Julia blog post, and if you just type Why Julia, well, that no longer is the right one. How about Why Julia blog? Okay. Google has down sample.
Probably the localization into Singapore context.
Yes, that might be it. So if you Google why we created Julia, so this was a blog post we published in 2012, and it was kind of a bit of a teaser because it talked about essentially that this conundrum of being fast and productive. So people were like, this is absolutely not possible. Like this is a law of nature. You cannot violate it. So we don't believe it. And then they all clicked and downloaded Julia and compiled it. Back then there were no binaries. And then they were like, wow, this really is fast and it is fun to use. Okay, let me start contributing. And what made it easy to contribute to Julia is, and which is still the case, is that Julia is what we like to call Julia all the way down. So most of Julia is actually written in Julia itself. That makes it very easy to write high performance code without actually having to switch to C or lower levels. You don't have to be a compiler genius to write to extend the language or to write a couple of contribute a couple of functions. And so everyone who started using Julia kind of was they're like, yeah, the core is great. I mean, this is really fast, but these 5 functions seem to be missing, and then they would find themselves writing it and submitting a pull request. Let me give a demonstration of why that is the case. So before we go there, I'm just going to point out, so this is the Julia website, julialang.org, and if you want to try out Julia right away, I don't know if there's a good internet connection here, but you just go there and pick the version, operating system, and whichever one you want. It's only a 50 megabyte download. You'll get a working Julia, I promise. And then once you get it, you just double click it and you get a REPL. So you can now type stuff into it, and you start with 1+1, and that's great. And now we sort of you start seeing why what's sort of interesting and different about Julia is because it's scientifically oriented. One of the first things I like to type when I start up Julia is this function called peak flops. And you notice there was like a little tiny delay after I hit peak flops, and then it kind of came through. And the second time it's faster, right? And the third time it's also fast. And this is because it's a JIT compiler under the hood. So every time I try something new, it's going to compile it and cache the compiled code. Once I have Julia running, I do peak flops. Okay, so this says that my laptop at its peak is capable of processing 64 gigaflops, so 64 billion floating point operations per second. Of course, no program ever runs at that speed except for peak flops. So that's how scientific. The whole goal of high performance computing is to have your program run as close to that speed as possible. Is this visible from the back? Should I blow it up a little bit? It's okay. Maybe one more. Let's just do a couple more. All right. Okay, so that's Julia. Once you start out, now like I was saying, so everything is Julia all the way down. So for example, let me just you can actually ask Julia what gets run when you do 1 plus 1, and in most programming languages you would not expect to be able to sort of drill down all the way, but instead in Julia we actually this is one of the first things I would show an audience, right? I'm not showing you how to use Julia. I'm actually beginning to show you how to look inside of Julia first before you actually start using Julia. So I did add to which of 1 plus 1, and it says, it's in that file called int.jl. So if I have, if I go to my Julia source tree, and I'm on master, so let me just check out and get to release 0.4, which is what this is. Okay. So then if I go to base is where all the Julia base libraries, so the Julia standard library is, and if I do, +8 int.jl, it should have that definition right there. So this is the Julia definition for 1 plus 1, and what's happening here is that it's saying if I add an x and a y, both of which are integers, add int is an LLVM intrinsic, which will actually generate the code. The exact assembly instruction that's gonna add the two numbers, and then you're gonna unbox the two integers, generate the code, and then box the result, and then the compiler, if it's able to do all its type inference and all its magic, it's gonna get rid of all this boxing, right? So just like any other dynamic language, and so you say, okay, that's fine, but let's look at what actually happens. So you can actually look at the assembly completely interactively by saying add code native of 1 plus 1, and it's kind of doing what you'd expect. There's a bunch of pushing and popping of the stack, and then there's the one add instruction, and you can do this for more complex functions as well. So let's say I have a function. So this is a simple syntax for writing functions in Julia. f of x comma y comma whatever equals something, and I just wrote this function which is x cubed plus x squared plus 2. And now notice I haven't mentioned the type of x anywhere, right? So it's dynamic now. It's depending on what I give it as an input, it's going to do something. So if I give it a floating point value, I get a floating point result back. If I give it an integer value, I get an integer result back. And just to make sure, we can check. So there you go, and let's just make this 2.1. All right, so you got a float 64, and then you can kind of look at the code that it generates just to get a good sense of what's going on under the hood. Right, so you can see that the actual assembly code it generates for the version that takes an integer versus the version that takes a floating point value is qualitatively different. And this is, after all, when you talk of why is Julia fast, or why is something fast, it's always fast because it generates a tight assembly code that can run really well. And that's what happens in Julia under the hood as well. But the beauty is that it takes code written in Julia like this. So you could have gone ahead, created a new integer type, and defined it to do completely something different, right? And you will get benefit of the same, all the benefits of the Julia compiler, and get this tight assembly out of your own code. And Julia has many other tools that will allow you to look at your code and figure out where issues occur, where type issues occur, and so on and so forth as you write more and more complex code. So I don't want to go a lot more into the compiler of Julia or why it's fast, but this is just to give you an idea of what it feels like to start being a Julia programmer. So, if what do you like? For example, if you're a scientific programmer, you want random numbers, and you want random matrices, and you want to have large random normally distributed something like vectors, right? And this was 10 to the power 6. How about writing a simple function which just does, for I equals 1 colon n. Okay, let's just. You like the REPL editing on the live editing on the REPL itself? That's kind of fun. You can just write whole functions here. 5 more minutes. Okay, so I'm going to write a very quick function here where I'm going to take an array A and I'm going to calculate the sum. So let's just say s equals 0 and then s plus equals ai end. And so if I give this function an input like x equals rand of 10 to the power 6 and then foo of a, I'm going to time it. Oops, it's x, sorry. And this has to be the length of, sorry, this is what happens when you you always mess up a few things. So there we go. So I actually was able to write a loop on an array of 1,000,000 elements. So this is something you can absolutely not do in R or Python or any interpreted language, right? Because you would never loop over something in a for loop going from 1 to 10 to the power 6. But in Julia, you just do that. You don't think about it. You just write your code. You know it's going to generate that nice assembly. You run it the first time. You see that all this garbage collection happens because the compiler is generating a bunch of garbage as it generates your code. But then the second time, it's the minimal allocation. It just allocated 160 bytes to do this work, and it ran in almost 100 times faster once it was compiled. And this is about the kind of timing you would expect if you wrote a C function doing exactly the same thing. In fact, Julia will auto-vectorize and generate SIMD instructions and all that good stuff if you do it. So this is the core of the language, and what people begin to use this kind of stuff for is, and what I'm not showing you at the moment is stuff like, actually maybe I'm just going to show you for the last minute before I. So if you go to juliabox.org, you can run Julia on the cloud completely from the browser. You just log in with any Google account, and there we go. So starting from a language that is simple and very basic, people have built, we have about 1,000 open source contributed packages at the moment, and you can load gigabytes of data into Julia. You can analyze it on your laptop out of core, or you can load it on a distributed cluster. You can load up gigabytes or hundreds of gigabytes of log files, run whatever it is that you want to look for in log files. Often I hear that people are aggregating, right? You're just counting events, but how to go from counting to prediction, for example, right? I have a large data center, I have all these log files, I'm monitoring these events, I'm collecting all this stuff, but now I want to write a little machine learning, I want to write a little regression, I want to fit some data, I want to see, this is my hard drive failure time, when do I think the next one's going to go, or which one's going to be. So it's very easy to sort of start crunching data, building a model, and fitting data, running it in production, and having it all be live in real time. And it's not that Julia is great for processing log files, it's just that Julia happens to be a great language which has a lot of fantastic mathematical tools, machine learning tools, and is incredibly fast. So you combine all this and you can imagine applications that are otherwise pretty hard to do. Let me just show the kind of rich graphics, for example, that you can pull off in Julia. As this page loads up, what I'm going to show is Julia using Python's plotting capability. So Python has beautiful plotting capabilities. It's in a library called matplotlib. We didn't reinvent the wheel, we just reuse it. And so this is, you can generate all these kinds of fancy graphs and plots in Julia by interoperating with Python. It's pretty trivial to call Python from Julia, Julia from Python. In fact, a common party trick is Julia calling Python, calling Julia, calling Python, and you can kind of go as deep as you'd like. And the kernel died, so that's a good sign. All right, so try it out, download it, and let me know. Throw us a line on Julia users about your experience, and hopefully you guys will become Julia users. Thank you.